have a very international speaker with us, Dr. Rajesh Singh. And first of all, on behalf of Indian Institute of Technology, Palakkad and IEEE APS Society Kerala chapter, we thank you a lot for giving your valuable time and to share your thoughts and deeds with us. And we are very fortunate to have you today. So let me introduce formally our speaker today. So Dr. Rajesh Kumar Singh is currently a postdoctoral researcher at the Microwave and Radiation Laboratory, Department of Information Engineering, University of Pisa, Italy. He has received the BTech degree in Electronics and Communication Engineering from Uttar Pradesh Technical University, Lucknow in 2010, and MTech degree in Microwave Electronics from Delhi University, India in 2013. He received his PhD degree in Telecommunications Engineering from Bharati School of Telecommunications, Technology and Management, Indian Institute of Technology, Delhi in 2018. His current research interest includes design of reconfigurable antennas for current and future wireless system and body-worn antennas for near and far field UHF RFID readers. He has published more than 30 international journal articles and conference contributions. He has served as chairman between 2016 to 2018 and treasurer 2014 to 2016 of IEEE MTTS Society, Indian Institute of Technology, Delhi Student Branch Chapter. Dr. Singh was a recipient of the Young Scientist Award for the International Union of Radio Science, General Assembly and Scientific Symposium, that is GAS 2020. So, Dr. Rajesh, I welcome you. And before you start, I would like to request our Chairman of APS Society Kerala chapter, Professor Abdullah, to say a few words, and then you please start with your presentation. Your talk. Yeah, Professor Abdullah.
Okay, fine. So the thing is that it is better to talk as a vote of thanks, right? Anyway.
Yeah, you will also do that.
The thing is that, our Kerala, we are celebrating Onam tomorrow. Yes, and I hope you may be knowing that. It is one of the, I should say that is a national festival in Kerala state. Right. All community, they will celebrate this. And that is the reason today participants are less in number. Okay. So anyway, it's a nice introduction, Dr. Rajesh Kumar Singh. And I hope he has a lot of practical experience in designing, as you said, the wearable antennas and RFIDs. So I hope he will share his experience and exposure to the participants. And of course, now our programs, this webinar is a continuous series. Every week we are expecting, and parallelly, our student branch APS societies, we have 5 student branches in Kerala, one in Cochin University itself, then IST, then Government Engineering College of Barton Hill, then Musliar College of Engineering, and Ahelia College in Palakkad. And our IIT Palakkad, you haven't started a student branch there. But what I'm going to tell you that all these 5 student branch together as a conclave, they are going to have a big program during this September 18 to 20, a 3-day event. Okay. So already I have given my green signal and our full support. I hope all you can enjoy, because they are inviting people from outside India also for this program. And regarding this, Sukumal is doing a wonderful job. Of course, as a vice chair, and he is leading in this. and he is bringing a lot of people from across the globe, not only in India. And I extend my sincere gratitude to Dr. Sugmore.
Thank you.
And
Thank you so much.
we continue this process, so that at this pandemic situation, all our scholars and young faculties, they should get motivated. It's a nice opportunity to them, because normally if this pandemic is not there, nobody will be coming from abroad, and like people like Rajesh and we won't get, isn't it? Because we need to give him a big huge amount of travel support, and so anyway, it's a good start, and I extend my sincere gratitude to Sugmore and his team, definitely. And
Thank you so much.
I think we can start.
Yes.
Okay, carry on, Dr. Rajesh Kumar Singh.
Okay, so thank you so much. So first of all, I would say thank to IIT Palakkad and IEEE APS Society Kerala chapter, and especially Sukomal sir for giving me this opportunity to share my work at this platform. So today I will discuss some research on development of body-worn antennas and their challenges. So in this, I will start with a little bit introduction about wearable antennas. Then I'll focus this wearable antenna for a particular application like UHF RFID system, which are in demand. Then I will discuss about design consideration and challenges of wearable antennas, how we will make it, and how first thing is how we will decide and what we have to make it. So all these things we will discuss in this talk. EM aspects, we will see how we will simulate this type of antenna and what kind of analysis we have to do for such antennas. Later, I will show some prototype, wearable prototype, then measurement setup. I will show the measurement setup, how we will characterize these antenna experimentally. Later on, measurement of antenna parameters and near and far field, because it is important parameter, because we have to think that we have to measure this antenna performance in near or far field. It is depends on application where we have to put this antenna. Later, I will conclude my talk with summary and some references which I used for preparing this presentation. And I'll also discuss research activities at my university. So first thing is wearable antenna. Why is it really needed? And if it is needed, then for what application we need wearable antennas? So we will see later after the talk. Wearable antennas have gained much attention in recent years because of their attractive features and possibilities in enabling lightweight, flexible, low-cost, portable wireless communication and sensing. So what are the requirements for wearable antennas? Such antenna need to be conformal when used on different parts of the body. So thus need to be implemented using flexible materials and designed in a low profile structure. So in terms of performance, these antennas need to be capable of operating with minimum degradation in proximity to the human body. It is an important thing because when we design an antenna, if we have to put this antenna on a human body, then the performance will degrade. So we have to analyze that what type of performance and how much it is degraded. So, and we will see the applications of wearable antenna. Here I'm showing one picture. Here a patient is lying on a bed in a hospital. So you can see there are leads which are connected to the human body. There are a lot of leads. So do you think that this patient can move? I don't think so, because there are a lot of leads. If we could able to remove such leads by introducing some sensors, then we can increase his mobility up to some extent, not fully, but we can increase mobility of this patient by using sensors. Other applications are in sports and fitness activities. In fitness activities, the smart watches, smart glasses are available nowadays. In military and security, gaming and entertainment, smart clothing, industrial and enterprises, etc. There are various applications. Starts from small thing like glasses to even GPS enabled shoes. So regardless of the application area, an important aspect of wearable communication is the preservation of antenna performance. So these antennas are used in body area network for wireless communication. So to establish the link between a body area network, we need small flexible antennas for it. So what are the requirements for such antennas? Smaller size, lightweight, least affected by human body, almost maintenance free, ideally comfortable to the body of antenna, and durability are required to fulfill the above needs. So wearable antennas in such technologies need to be conformal because it would be put it on a human body. So when human body move, then antenna should move. So we need low profile structure and flexible. So considering the easily available flexible textile as a dielectric material, why? Because the cost of the antenna become very low. Also, the development of the planar technology has boosted the research in this particular domain nowadays. So what wearable antenna do? It actually increases the freedom from a designer point of view, as well as their ability to conform to the body surface. Furthermore, their omnipresent monitoring capabilities make them extremely suitable for demanding application. So I will discuss some particular application for wearable antennas because this is a very big subject. So we will narrow down this topic for a particular application so we will discuss wearable antennas for RFID because it is a current research subject and exploring. So with the advancement of electrotextile and conductive wearable materials, there are a lot of work done on the wearable reader antennas or tag antennas for body area network and RFID. So first thing is, what are the challenges in designing such antennas? So first thing is, it's very important human body near field effect because this antenna will be put it on a human body, so it will affect and it will definitely degrade the performance. So it should be insensitive to the near field effects to prevent any harm to human body because for this there are SAR regulations also. We will discuss later. Compactness is the second thing. Wearable sensors must be flexible and confined size rigid antennas. Such limited sensor volume sizes makes the design of wearable devices more difficult and seamlessly into clothing because we know that if we make it antenna compact then efficiency would be degraded. So this is the trade-off between performance and size. What the next parameter is desired radiation characteristic. What type of characteristic we need for such application? Because for different application we require different radiation pattern or different polarization. So we have to decide first to how and what we needed actually before designing any wearable antennas. So it must be low cost and lightweight. Next thing is the stable performance. So what it means by stable performance? Suppose we make an antenna and put it on a human body, then if we repeat this antenna measurement, then it should be more or less similar. It should give similar results. Suppose there is an error, maybe air between antenna and human body, then it will affect the performance because of dielectric. If dielectric is changed, then the resonance frequency will change. So to confirm the stable performance, then we can say that this antenna will perform better. There are FCC regulations on SAR value. SAR is the specific absorption rate. So whenever we put an antenna on a human body, so if it radiates, then human body absorbs energy. It would be harmful. So there is a limit. We cannot increase power beyond that limit. So next part is impedance matching and antenna detuning. So what happens? You can see in the left hand side picture here. This is an antenna, textile antenna printed on a cloth. So it is in air. Now we put this antenna on a glove, then human hand will be in the picture. So human body affect this performance. So we will see later how much it will change the performance. So size, cost, and weight I already discussed. So bending and stretching. It affects much the performance of the antenna in terms of reflection coefficient, radiation pattern, and gain. What happens when we bend or stretch this antenna? Because you are seeing here, this is antenna integrated on a glove on a hand. So if we bend this hand or stretch, this cloth is stretched, then performance will degrade. Antenna position. Sorry, antenna position need to be investigated, because first we have to understand that where we will put this antenna. So we can understand before putting this antenna that how it, if we bend this antenna, then how much performance will be degraded. Because if we put on a hand, then if we bend or stretch this hand, then antenna will not be affected much. Suppose I make this antenna on a hand finger, then what happens? If we move finger, then the polarization will change. Suppose this is the polarization horizontal, and if we change the bend of this finger, then maybe it will be vertical, so it will be a cross polarization. So we need to understand first that what is the antenna position and what type of radiation pattern and polarization we need. Sensitivity, if the distance between the antenna and human body changes, then what happens to the antenna performance? As I told that if there is an air gap, then effective dielectric constant will change. So it will change the resonance frequency. So input impedance is changed, then we cannot transmit power to this antenna because it will reflect if it is not at the resonance at the design frequency. Safety guidelines are given by US and European Union. So SAR limit is 1.6 watt per kg averaged over the 1 gram of tissue. European Union has a different limit. It is 2 watt per kg average over the 10 gram of tissue. India also use the US limits. So what are the analysis required for such antennas? Suppose we have to make a wearable antenna, then first thing is we have to model the human body. Suppose I want to put this antenna on a human hand, then definitely we have to model human hand first. So how we will model the human hand? So here I am showing some tissue layers, skin, fat, muscle, bone, and I'm taking some thickness of these tissue layers. Then what are the conductivity and what are the dielectric constant of these tissue layers at different frequency, because it is important. You are seeing here 868 megahertz and 2.45 gigahertz. So the conductivity is changed as frequency change, and dielectric constant also. So it is important to first know what are the conductivity and dielectric constant. So we can put these things and model this hand to simulate an antenna, because before making an antenna, suppose I design an antenna on air, if I put it on human body, the resonance frequency completely will be changed. So first we have to understand that what is going on. Because of lossy nature of human tissues, gain of the antenna reduces. As we know, human body absorbs radiated power. So here I'm showing two blocks. Here you can see antenna put on a lossy block. We can model hand as a lossy block and antenna on air. So there will be a degradation in efficiency, and maybe radiation pattern will also be changed. How we will calculate the SAR? So SAR can be easily calculated in any full wave EM simulators. We have to put mass density of the body tissues, and we can calculate SAR by calculating power loss density. So effect of bending and effect of stretching we can easily see before designing this antenna. Means You can see in the full wave simulation. So the next part is the measurement. Again, it is necessary to measure the performance of the antenna when antenna is in proximity to the human body. So we will see all these things later. I will show by giving one example. Here there are some manufacturing process. I put some manufacturing process here: fabric based embroidered antenna, polymer embedded antennas, microfluidic antennas with injection alloys. So here we can see fabric based embroidered antenna. So this is the E-shaped patch antenna. So here it is shouldered by a coaxial connector. Center pin is connected and backside there is a ground plane. So here we can solder it because there is a conductive part, or we can uh, put epoxy kind of uh, layer to connect this coaxial connector to this antenna. Here polymer embedded antenna, we can see here there is a band. So band view is showing. So we can band this antenna, but it is not showing here that what would be the performance if we band it. So we will see later. Inkjet printed antennas and screen printed textile antenna. So here I am showing one zoomed view of near the coaxial connector. What is there? Cracks on the surface of the antenna washed 20 times. So there is also another point which has to be considered before, because if we make antennas like wearable antenna on a cloth, then we will wash it and again we will dry it. Then what would be the performance after 10 wash or 20 wash? So what are the issues here? Connector detachment, you can see here in these tracks are breaking. So what happens by doing this? Increase ohmic losses. So if in ohmic losses will increase, the efficiency will be degraded, gain will be less. So what is the solution? So solution for this is coating with a thermoplastic material. So we can reduce this effect up to some extent. So these are the comparison of different advanced manufacturing techniques of wearable antennas. So depending upon the parameters, what we need, what we require, we can choose the technique. Cost to fabrication, robustness to wetness, robustness to bending, fabrication simplicity, weight and frequency. So according to these parameters, we can choose the manufacturing process. Textile antennas are a special class of antennas that are partially or entirely made out of textile material. So here I am showing two types of fabrics. One is dielectric fabric, another is conductive fabric. So normally cotton, polyester, silk jeans are used as a dielectric fabric. Zelt, flectron, copper, polyester fabric are used as conductive fabric, because for ground plane and patch we need conductive fabrics, and in between there is a dielectric, so dielectric fabrics will be used there. So there are some other factors influencing the antenna performance also. Till now we saw the influencing performance parameter in terms of antenna, but now these are the parameters related to the substrate which we are using. So thickness of the fabric, which is should be uniform. Complex permittivity of the material, dielectric fabric has a complex permittivity. So what are the losses in the imaginary part? So these are also affecting or influencing parameter for the antenna. Surface resistivity of the conductive textile, because it is not perfectly conductive. So there should be a finite surface resistivity, and it is directly related to the conductivity. So we can calculate the conductivity and we can see what are the resistivity. According to the resistivity, we can measure or calculate the losses. Loss tangent, mechanical deformation of the fabric. So yeah, this is an important parameter because this is a fabric. So after use this fabric, mechanical deformation can be happen, because if we bend stretch this antenna or cloth again and again, then will degrade. So there are various methods to calculate the electrical properties of conductive textile. we can calculate accurately by using these methods. So I'm showing one here. There is a reference which is guidelines for the choice of materials for the design of textile antenna. So if anybody is interested, then there is a good reference I'm writing here, so you can understand what are the how we will choose the material for such antennas. So let's focus down and narrow this topic of wearable antenna into application for RFID. RFID technology has widely been deployed for short distance communication. As we know, RFID has 3 different bands. It is in kilohertz: 125 kilohertz, 13 megahertz, and 900 megahertz. So 900 megahertz are used extensively nowadays because it has a high data rate compared to the low frequency bands. So particular interest are RFID system for IoT based personal healthcare application, and specifically those applications where RFID antenna and sensors are integrated in a smart glove. So we will see the antenna integration in a smart glove. So there are various applications for RFID. We know these applications. So what are the components in RFID? There is a RFID reader antenna, there is a RFID tag antenna, and there is some interrogation or computer, so some signal processing thing. So for antenna designer, we can make antenna for a RFID reader or for RFID tag. So 2 types of antenna can be made for our UHF RFID or any RFID system. These are some pictures of UHF RFID systems because these antenna are at around 868 megahertz because it is an European RFID UHF band. So these are some pictures, and these are the antennas. In this previous slide, this slide has these are reader antennas, and these are some tag antenna. So you can see here, mostly dipole antenna is used for tag because it is simple and we can compact it by meandering lines. We can see here in these pictures. So wearable antennas for RFID, I just put some antennas just to mention that it's type of antenna already designed. So in the left hand side, there is a loop antenna here. So this is an interdigital capacitor at some periodic distance we put here to make it current uniform, because this antenna at 868 megahertz has a big length. So the perimeter is approximated to lambda. So what happens, there is a current null at lambda by 2 distance. So what happens, the magnetic field strength would be low because of this out phase current. So we have to make it in phase current by introducing this capacitor in between. So we can make it in phase current so we can get a strong magnetic field near this. Yeah, there are also some tag antenna here, left hand side. This is a printed dipole tag antenna. So these are printed on a substrate. These are not actually wearable. So to make it wearable, we have to choose a substrate which should be flexible. Like here, you can see here dipole antennas integrated in a glove. So this is very small antenna you can see here. So these are for RFID tag. This is the antenna which is designed for RFID reader. So this is like quasi-Yagi antenna. One is a driver and 2 are the parasitic elements, reflector and directors. So this antenna is actually 100 mm by 100 mm, so 10 centimeter by 10 centimeter. If we want to put it on a human hand, then it is large. We cannot put on a human hand because the approximate size is 6 centimeter by 6 centimeter for a normal human. So for a glove integrated antennas, there is a possibility to make it RFID reader antenna for a integration on a hand, there are two possibilities. You can see here, either we can put it here or we can make it here, like a bracelet antenna. So non-flexible antenna has a printed substrate, but flexible antenna has some flexible material, or we can make it on a cloth or some flexible type dielectric material. So here I'm explaining the application scenario. So what is the application? Here we have to make a RFID reader antenna, which would be placed on a human hand, and we need to detect some tagged objects or tag which is very near, around 30 to 40 centimeter, as you can see in this picture. At the same time, we want to avoid some tags which are beyond this range. So we want to use this antenna in the near field. So what we will do, we need a compact antenna. We will place, we have a two position, we can place it here or here. So after that, if we design an antenna here, then how we will connect it? There are portable RFID readers. So we can put portable RFID reader here, or we can put it here. So then we can connect this portable RFID reader to this antenna, and we can radiate, and we can detect tags or tagged objects. So here, this is a picture of RFID reader, portable RFID reader in the left hand side. So one kind of reader is this, another kind of like watch. So to choose antenna for such application, there are various antennas available, like loop and solenoid antennas. In this picture, this is a solenoid antenna. So this is like band, 2-turn, 3-turn, 4-turn antennas. What happens in such antennas? The field strength is same in the front and back direction. Along the axis, the field strength is same, more or less same. So what we want here, we want to reduce the radiation from back side along the hand, and we want to increase this radiation along the hand finger. So we can detect objects here, and we can save battery life. Because this particular application is for labor which is working in a warehouse or in a company, so he will work for 7 to 8 hours. So the battery is a requirement, so we don't need to recharge battery again and again in a single day. So at least this battery will work for a single day in a one charge, then it will be a beneficial for company and for that worker. So what we will choose? We will choose a design layout like that. We will reduce some radiation in the back side, and we can increase the radiation along the hand fingers. So we know the Yagi-Uda structures. So we will put Yagi-like structure on the hand palm, because the radiation we can modify by using reflector and director. So here you can see there is a straight dipole here in the left hand side. So I bend this layout in a rhombus shape. So you can see here this type of structure. Now this is compact one, because we know the application and we know the position where we have to put it. So we will make this structure to fit on a hand palm. So we bend it. And another thing is, why we bend it? Surface current which is traveling on the periphery of this, it will be in the in phase. So this is a requirement to get a strong magnetic field above this loop. So for this particular application, we need magnetic field strength higher along the hand palm and along the hand fingers. So this rhombus shaped loop will give us the magnetic field strength along the hand palm. So to bend this, we will get a strong magnetic field, and by using parasitic elements, we will get higher field strength along the hand fingers. So we can see here one director is connected. And we can see this is the printed antenna. Conductive threads are here, and there is a cloth. So this is normal cloth, stretchable fabric is here. So this antenna is connected through a balloon. Balloon is balanced to unbalanced line because we cannot feed it directly by using coaxial connector. This is a sequential feeding. This is a actually balanced feeding, not sequential. So here we are seeing the reflection coefficient in each case without hand and with hand. So we are seeing here with hand, there is a little bit shift in the frequency because there is a hand effect in the reflection coefficient. We can see here. So frequency little bit shifted, but it is not shifted much because we considered these things in the simulation already. So it is more or less minus 10 dB and below the reflection coefficient. So now the SAR calculation, we can calculate the SAR. We know the formula to calculate SAR in the EM simulator. So we know the limit in the, so we can easily calculate. So I'm showing one picture from EM simulator. So we can put material density in the EM simulator and calculate power loss density. Then we can easily calculate the SAR value for this particular antenna. So this is the electric and magnetic field strength. Here we can see this is the strong magnetic field along here and here. And with one director, you can see here in the along the hand finger, the field strength is high comparing to the back side. We will modify this layout by putting one reflector later. Here I'm showing the measurement setup. So how we can measure this type of antenna. So I am showing one solenoid antenna here, which is connected to this coaxial balloon, and we can put RFID tag in the horizontal and vertical direction. So this solenoid antenna is connected to the RFID reader, and we can actually measure the RSSI, received signal strength indicator. So we measure RSSI in such antennas. So we can detect the tag. So we can calculate the distance, how much the tag is detected. So these are the prototype. There are two solutions I'm showing here. You can see here one solution is a little thin and another is thick. So two types of material and different conductivities we are using in these prototypes. So the first one is, we can understand that this is thin, so it is durable, because if it is a very thin, then it is less affected by bending and stretching. So solution 1 is better than solution 2, but solution 2 has a good conductivity, better conductivity compared to the solution 1, but this is a trade-off. We will go for solution 1. And also this antenna is compared to the copper tape antenna. The cloth fabric is the same. We put one copper tape here and compare the performance of both antenna. So durability is higher for this conductive antenna, textile antenna, because if we wash it, then the copper tape will be removed. So the solutions are better than compared to the copper tape antennas. Now the another thing is the connection or connectivity, how we will connect this antenna or how we will feed it. So here we are seeing snap buttons. Can we solder a SMA connector here? I think no, because this is a cloth fabric. If we heat it, then it will burn. So we cannot fabricate, we cannot solder it. So we have to put snap button. So snap button is like one is the male part, another is female part. So the male part we can connect to the reader side, portable reader side, and female buttons can be put it on the antenna side, so we can connect it later. And this connection is already tested. So up to 3 gigahertz, snap button works well up to 3 gigahertz. It has some insertion loss, but it is acceptable and fulfill the requirements for our application. These are the read range we calculated from RFID reader. So read range is calculated along the hand finger and along the arm. So we can see here clearly in the back side this is 22 centimeter and in the front side it is 29 centimeter, 27 centimeter. So it is more along the hand finger. And this is the measurement by changing the transmitted power from the antenna. So we can actually measure the read range by changing the transmitting power. So we want to reduce the transmitting power because later on we will use battery. So if we make it such antenna efficiently, then we can reduce the power, input power. So battery can work up to more and more hours. So this is the modified one. So one reflector is used. So what happened by if we put a reflector here, then the read range along the hand finger direction is increased more. So here we can see the magnetic field strength and electric field strength is higher comparing to the back side. Again, we calculate the SAR value. So for this antenna, for this particular antenna, the maximum allowed transmitted power is 27 dBm. But in this particular application, to get 30 to 40 centimeter read range, we only give 17 dBm power. So we are giving very less compared to the acceptable. So we are saving the power. So here we can see the read range 40 centimeter in the fingertips direction and 17.5 centimeter along the human arm. So somehow we reduce the radiation along the human arm, which we wanted. So these are the bending effects. So we put this antenna. So make a cylinder. In simulation, what we can do is we can put one cylinder and we can bend it. So at different bends, we can see the reflection coefficient, input impedance. So it is not changing much because the antenna is on this side. So if we bend it, it doesn't affect much. That's why reflection coefficient is not changing much. But it is not true for each and every antenna, because if we put antenna somewhere else, then if we bend it, then it will affect much. Stretching is we are considering three scenario here. One is straight hand, another is some bend, and third one is the closed palm. So we can see here the reflection coefficient. So there is a little bit shift in the frequency, and this is because of when we stretch this antenna, then what happens? There is a distance between the driven element and parasitic element will change. So by changing the distance, our loading effect or capacitance actually changing, so frequency change. So this is the comparison of various layouts of reader antennas. We make this particular antenna for one director, two director, one reflector. So we compared all these results in this table. So there is a trade-off. We go for one reflector and one director because the size of this antenna would be easily fitted on a human hand. For a normal human hand, we don't need to make these antenna for different people. So this 7 centimeter by 6.5 centimeter will be fitted for normal human being, and it is fulfill our requirements. So application scenario 2, if we increase the function of this antenna, suppose I make this antenna dual band or wide band, then what will happen and what we need more in the simulation and measurement. So first thing is we know that we will increase complexity because we are adding function. So the another thing is we are adding two frequencies here. One is 868 megahertz and another is 2.45 gigahertz. So the application is we will collect the transmitted data at 868 megahertz, and we will transmit back to a WLAN link, which is at 2.4 gigahertz. So for this, we need dual band antenna. So the important thing is not the design, important thing is how we will analyze it. So for analysis, we will see the input impedance. So we can see here there is a two bands. One is at 868 and 2.45 gigahertz. Here I'm showing the picture, the textile antenna, which is dual band here. Again, it is fed by balanced feed. And there is some this reflection coefficient plot. So here we can say that this is dual band antenna, perfect resonance at two frequencies 2.45 and 868 megahertz. So the important parameter is I'll show one reflector is placed here. So again, we did the same thing what we did for single band, but for the analysis, what in the previous antenna, what we did simulation for single band. So we know the 868 megahertz, what is the conductivity of human hand and the dielectric constant. But what happens here at 2.45 gigahertz, dielectric and conductivity will be changed. So how we will simulate this antenna? We will simulate this antenna. We will consider dielectric constant and conductivity at 868 megahertz. And the next simulation is for 2.45 gigahertz, we will change the dielectric constant and conductivity. So everything will be changed. So will little bit complex in the simulation point of view. But we need to do this because if we simulate it 868 megahertz with the same conductivity and dielectric constant, it won't work at 2.45 gigahertz. So we should consider these things. And for wideband also, we need to require to simulate it with different frequency, with different dielectric constant and the conductivity's value. So these are the challenges, simulations. So read ranges, again, we are showing here. So again, it is the higher along the hand fingers and reduce in the backside direction. This is the radiation pattern. In the previous slide, in the previous antenna, we don't need to mention radiation pattern because we were working in a near field. So near field parameters are electric field strength and magnetic field strength. The far field parameter, here we are using this antenna for dual band. So 2.45 gigahertz, we need this antenna to work in the far field. So we have to see the radiation pattern at the far field for such antenna. And there is a plot, gain versus sheet resistance. So I discussed the surface resistivity earlier. So this is the sheet resistance of the material. So if we increase the sheet resistance, then the gain will decrease. So our antenna, this antenna is a 0.4 sheet resistance. So gain value is a minus 0.6 dB. So there is a trade-off. If this is not very conductive antenna, then gain will be decreased. So as per the summary, we discussed the variable antennas, discussed the challenges in designing body-worn antennas, discussed the design consideration of such antennas, what are the things we should consider before to design any particular antenna like this variable. Discuss numerical and experimental characterization by taking few examples, and the fabrication technologies. We saw the various fabrication technologies are available, and if anyone is interested, then it can go for the reference. So there are a lot of technology and we can choose the material accordingly. So there are benefits of body-worn antennas. We can put it in the human body and it is flexible, so we can move our body freely. These are some references we use to prepare this presentation. And there is a special section announcement, electric and magnetic coupling for near field systems. So if any researcher is interested, so they can submit the paper in this special section. This is a new journal. And guest editor is Paulo Nepa, University of Pisa, is my mentor, and other three are also the guest editors. Submission deadline is November 10, so if anybody is interested, can submit. This is the Microwave Radiation Laboratory Group, RFID system team, Professor Paulo Nepa. There are two assistant professors here, Andrea Michel and Elisa Bufi. And there are two PhD students and some other master students. So this is not very big team, but very active team for RFID here. There are other research activities here for LTE 5G cellular antennas for cars. So there are various projects. They are making reconfigurable LTE antennas for car roof or car backside. So there are various positions we can put antenna on car. Localization of RFID, near field focused microstrip arrays, wearable antennas for body centric communications, antenna design for wireless communication system at UHF and microwave frequencies. So there are various projects available, and all these things are with the collaboration with either SMEs or international research centers. So there are various projects are going on. So thank you for your interest and kind attention. Yeah, I finished.
Thank you for presenting, for giving a nice presentation. And we'll take a few questions.
Yeah,
and
sure.
I am just telling the questions from the chat box. So few questions are, one of the question is, which dielectric constant will use average of the two values? Even the question is not clear to me. So the final here, whenever you are realizing this kind of a, this kind of antenna, which dielectric constant generally we should use? Probably this could be the question.
Okay. So I will say there are modeling techniques.
Professor Anu Mohammed, if you are present, you can directly ask the question to the speaker. Participant can directly ask the questions by unmuting their microphone. Okay, I think he's not here. So I'll go to the next question.
So yeah, he can listen. Actually, I will say something about this. So there are different modeling techniques. Actually, you can model this human hand by using a single layer. But here I already shown that there are 4 or 5 layers. So we should consider each and every layer in the simulation, because each layer has a different dielectric constant and at different frequency it is changing. So it is better to make it model like this, that we should consider each and every dielectric constant for each layer. If we took average, then there are various methods by taking average dielectric constant at frequencies, but we should consider dielectric constant and conductivity for each layer. So, and again, I would say that I mentioned the layer thickness. So 2 mm thickness we consider for a skin, 2 mm thickness we consider for fat, but it is not true for every human being. So we can, if we change this thickness, then performance will little bit different. So you can also change this thickness by making parametric analysis. So you can see the changes in the reflection coefficient and input impedance. Yeah, but I will suggest that you should consider the each and every layer dielectric constant and the conductivities. Yes, I finished question. Sorry, sir, your first unmute then, please.
Sorry.
Yeah.
So is it possible to increase the inductance without meandering the microstrip line?
Yeah, Actually, there are various techniques to increase inductance. There are defected grounded structures available. But here you can see in this design, there is no ground plane. In such antennas, dipole antenna, the other arm is used as a ground. So in this structure, we cannot increase inductance like DGS type structure. We can make it, we can remove ground plane in the backside of transmission line, then we can increase the inductance. But in such cases, or like this particular antenna, we cannot do this. Yeah, so please, next question.
Hello, sir.
Hello.
Hello, sir. I am Arun Raj.
Yeah, please.
Sir, for implantable antenna, which kind of battery is suitable for this applications?
Yeah, sorry, pardon. Can you please a little bit loud?
Hello, sir. Audible?
Yeah, please.
Sir, for implantable antennas or wearable antennas, we are using batteries. It will affect that antenna performance. Which battery is suitable for implantable antennas and wearable antennas?
Actually, can you type your question in chat box? I actually didn't understand.
Okay, sir. I already typed in the chat box.
Okay. So I will request to Komal sir to read this question.
Yeah, so actually I had some problems suddenly in the internet issue. So my call had deleted. So I request Mr. if you can read out the question.
Yeah, I will tell you what you was asking. In the wearable antennas, you are using some batteries. That is what he said. Will it affect the characteristics of the antenna when you place the battery there? That is what he's asking.
Okay. Actually, okay. So what we will do, we will put battery not on the antenna. We will put battery. I show one watch type structure. So there will be a portable RFID reader like watch. So we will connect this antenna to here by using this snap button. So this battery will be far, so it won't affect much. Yeah, it will definitely affect the backside radiation, but it is little bit far, so we are expecting that it won't affect, because the complete antenna product is not, we didn't receive it, but yeah, the company told that they checked this thing, so the antenna perform better. So
I think Arijit, you may have some questions. So could you please read your question?
Yes, sir. Am I audible?
Yeah.
Yes, you are.
Yeah, like you are discussing about RFID applications here. Now, another aspect is like when we are going for this RFID sensors and maybe chipless RFID, one requirement is to design some wideband antennas. So whether it is possible to design some wideband antennas in this flexible substrate or textile-based substrate, or what are the challenges actually?
Yeah. Okay, so yeah, we can design wideband antennas in such flexible substrate. But what happens? I mentioned the conductivity and dielectric constant. So you have to take more time, or you have to give more time for such simulations, because you have to understand that, because the frequent conductivity is changed fast. Dielectric constant is changing slowly, but the conductivity of human tissues change fast. So you have to consider the conductivity. So for wideband antenna, if you consider 868 up to 3 gigahertz, then you have to simulate it by making step size by 200 megahertz at least. Then you can understand what is the gain and what are the requirements of radiation pattern. And if you are making this antenna polarization sensitive, insensitive, like circular polarization, then you will have a lot of issues at because to make circular polarized antenna in such a broadband is not easy. But I won't say that it is impossible. It is possible, but you have to make sure that polarization and radiation characteristic what you want, so you will get it.
Thank you, sir.
I request other participants, if they have any questions, they can ask to the speaker. We can take one or two more questions.
Sir, I have another question. Can I just?
Yeah, please.
Yes, that simulation is one part. So when you are going for this final testing of an antenna, maybe far field measurement, so how are you modeling this human hand or this tissue, or what kind of phantom model or whatever in the final physical testing, I mean?
Okay. So what we did actually, we measured this antenna in two conditions. One is on air. So we put this antenna simply on some cardboard and test it. Then the second thing is, which is most important, we put this antenna on a glove, integrated in a glove, and put in on a human hand. Then we measure this antenna with the human body. So not with the phantom, but we measure this antenna with a physical human. So I put this antenna on a hand, then I measure the radiation characteristic of this antenna and measure the gain.
Thank you, sir.
Okay, thank you for all participants for asking the questions. So once again, I would like to thank Dr. Rajesh for sharing his research work, and I'm sure that it has enlightened our minds. So, and finally, I would like to request Professor Abdullah to say a vote of thanks, and you can conclude the session. Professor Abdullah, over to you.
Yeah, okay. Thank you, Dr. Sugmo. And in fact, it was a really nice presentation. As all of you, we know that these RFID antennas and tag has become most popular and important apart from shopping malls and library. And as we know that it has become mandatory, government has made it mandatory for all vehicles, especially when passing through the toll booth and all. I think there is a lot of opportunity and potential to design and combat and in the latest these RFID tags and antennas. And it's a hot topic. And of course, you explored this area to the students, those who participated today, in a very beautiful and a nice manner with a nice, beautiful photographs. And thank you for sharing your views and your ideas. And definitely, I'm sure some of the research scholars will benefit from your talk. And in the meantime, I extend my gratitude once again to Dr. Sugmo for arranging such a beautiful event. And definitely, we should carry forward this as a series of events. Like, we need to keep in touch with all these research community together. And again, I will tell once again, the September 18 to 20, students' activities are there. In fact, even though it is students, it's a good, I hope it will be a good event. And all of the participants, I request participate in that. And Dr. Sugmo, you please arrange similar events in future also. So,
Absolutely.
Okay, absolutely. We need to keep in touch. And thank you for the speaker once again, and Sugmo, and all the participants. Thank you. Have a nice day.
So thank you so much for giving your time and help and giving me this opportunity to share my work here. So thanks a lot. And I know Sukomal sir from last 7-8 years. He's very active. So definitely he will plan some good activities in future. And if any student is interested in such research topics, then I can help through online. And I already give my email ID in the first slide, so they can contact me and I will surely help them. So thank you so much.
Okay.
Thank you.